We all know tower cranes play a major role in the construction industry to efficiently and safely lift large, heavy materials to great heights. However, these tall structures often pose significant problems due to wind load and load deformation that can compromise structural integrity. Hence, it is important to develop a better understanding of structural behavior of tower cranes using robust design strategies in order to reduce potential failure. In this project, a tower crane will be designed and simulated based on the requirements from the construction company. The objectives of this study is to study the impact of various wind conditions on tower crane structures using software. The second objective is to understand how lifting heavy materials can affect structural components of tower cranes using FEA software. To establish the FEM problem, the 2D geometry of tower crane is created using Design Modeler. The specification of tower crane involves the height of mast, which is 50 meter, the length of boom, which is 90 meter, and the distance between counter jib and mast, which is 30 meter. Once mesh process is completed for geometry, boundary conditions are defined for tower crane. To convert wind speed to wind force, the wind force formula is used by assuming drag coefficient is equals to 0.19 for truss structures, and area is 325 meter square. The specifications of boundary conditions are as follows. The fixed support is applied at two nodes located at the bottom of the crane. Load P of 2000 kg is applied at end section of boom. The counterweight of 4000 kg is applied to balance the crane, while varying wind loads of 766.6 to 6898.7 Newton is applied at edge of mast for wind speeds of 4.5 to 13.5 meter per second respectively.
From the simulation result, we obtained the tower crane experienced significant deformation and the stress under 4.5 mm wind load. The deformation peaked at 18,663 mm in red with the minimal zero deformation in the blue. The top right section shows the most displacement while the mass remains stable with the minimum movement thanks to its secure base. Stress analysis in the minimum decombination stress at the cable boom rate has the highest maximum stress, contrasting at the mast crane right profile with the blue color. For the maximum combination stress, the highest tension load at the left mast stress and the cable with the compressed load along the right mast and the boom stress. This finding emphasize the area of the critical stress distribution in the crane under 4.5 mm wind load, highlighting the importance of the structure stability and safety measures. At under 9 meter per second wind load, the tower crane showed the significant deformation and stress. The maximum deformation reached 19,037 mm at the top right section, increasing from the base candidate with the blue to the tip with the red color, with the top section most affected due to the greater wind exposure. Stress analysis revealed the maximum stress at the boom cable and the minimum stress at the right mast. Higher stress in candidate by transition color with uniform deformation observed at the cantilever and the left mast. Compression with the uniform under the boom cantilever and the mast shown in the green color, while significant stress seen in the red or orange origin at the boom cable and counter jib cable. Blue region along the beam in candidate lower structure stress. Lastly, under 13.5 mm wind load, the tower crane experienced significant deformation with the maximum of 90,860 mm at the boom cantilever tip and the minimum movement at the mast. The deformation gradually increased from the mast to the boom stress. Stress analysis show the highest stress value between 583.95 to 1230 megapascal at the top and the horizontal element, and the lowest stress The maximum combination stress distribute in candidate the lowest stress along the mast at negative 1671.2 megapascal, wind force on the cable ranging from the 198.89 to 1134 megapascal, and the highest stress at the left mast. The minimum stress is observed at the boom thrust, mast thrust, and the counter jib. In the conclusion, the structure analysis revealed that the tower crane exhibited significant deformation and the stress under the higher wind speed, particularly at the 30.5 mm per second, where the stress level approach or exceed the yield strength of the steel. This candidate the potential structure vulnerability and the need for the reinforcement at the boom thrust and cantilever section to ensure safety and durability. The crane stability remains robust at the wind load 4.5 mm and 9 mm per second, where the stress level are below yield strength, suggesting safe operating condition under the normal wind environment. Enhanced structure stability in critical area is crucial for maintaining the crane long-term reliability and safety during operation under very wind condition.